4 questions. Just take 2 minutes and truly, just turn to someone who's near you, chit-chat with them for a couple minutes, and come up with a couple of thoughts for how to answer these questions. Go ahead. Oh, you're there. Oh, you got a nice shot right there. All right, folks. Thank you very much. Let's come back together and review these. What is the formula for simple interest? And what does each letter stand for? So just what is the formula, Nancy? Wait, are you Nancy? I can't see your name. Yeah. Oh, Nancy. Okay, go for it. Yeah, I equals PRT. And what does the P stand for, Brian? Wait. Yeah, Brian. Yeah, it stands for principal. And principal is the actual amount that you invest. Oh, well, this is terrible. That's the amount that you put into the bank. There we go, principal. And then what's the interest rate, Megan? I'm sorry. What does R stand for? Yeah, rate as a decimal. Very good. So rate as decimal. And then what does the T stand for, David? Time. Time. And what? Hours. Not hours. Yes, I heard a whisper back there. Time in years. This is why we talk about the difference between these, because in PRT, T is always measured in years. That's important that it's always years and that the rate is a decimal. That's different from the formula for distance, rate, and time. So how about that one? What is the formula that relates distance, rate, and time? Roy? Oh, wait, that's not really fair. You weren't here the other day. Oh, yeah, D equals RT. So they look fairly similar, D equals RT. But they mean different things and the units are different. So what does the D stand for, Aya? Yeah, distance. And what is the distance in? What unit is distance in? Miles per hour. Well, distance isn't miles per hour. Distance would just be miles. Yeah, that's one possibility, right? It could be miles. It could be feet if the rate is in feet per second. It could be meters if the rate is in meters per second. It could be miles if the rate is in miles per hour. So that really depends. How about the rate? Well, what was your name again? Oh, Raheem. Raheem, what would be the rate? Yeah, well, no, you just said it. The rate is miles per hour, yeah. So it could be miles per hour if the distance is miles. And then finally, in this case, the time would be just hours. So it really depends on this one. So if you're going to do miles and hours, then it's miles per hour. If you were to do meters, then in physics, you often do meters, seconds, and meters per second. So in terms of D, R, and T, it depends on the distance unit that you're using. You just have to be consistent all the way across. So if you're talking about miles per hour, you can't put a time in minutes right here, which is what we saw in that problem the other day. Okay, great. How do you set up the mixing problem? Like mix X liters of 20% with 30 liters of 50% to make a 40% solution. How do you set up a problem like that? Someone like to volunteer? Generally speaking, yeah, go for it, Brett.
Is it like
Yeah, absolutely. You'd set up some sort of a bowl or bucket to make sure you know what you're looking at. So in this case, I'm mixing X liters of 20%, and then I'm going to mix 30 liters of 50%, and somehow I need to end up with a 40% solution. So yes, that's a very important way to begin, is to draw a little picture for yourself and your audience. How do I now finish this off and turn it into an actual equation? Well, thank you for your enthusiasm, Raheem. You've already answered. I'm going to call on Gabby here.
It's percent times value.
Yeah, percent times, in this case, liters. But you're right, it could be any value, whatever that value happens to be. So go ahead, Gabby. This equation would become?
And then it would be percent times value. Plus percent times value.
Yeah, so go ahead, tell me what the actual formula is. So like I already did this first one. It'd be 0.2 times X plus?
0.3 times.
Yeah, 0.5 times 30. So the 50% goes first. And then what's over here? Yep, 40% as a decimal. And how many liters do we end up with? We have X liters plus 30 liters. So we have? Not 40. It would just be X plus 30. Yeah, that's it. It just ends up being an algebraic, or an expression, so X plus 30. All right, folks, so there we go. This type of problem is really bread and butter for this class. You'll see it on your take-home quiz tonight. At the end of class, I'll give you your first take-home quiz. And you'll definitely see a question or two like this on the test. So this is well worth memorizing, how to set up a mixture problem or a interest rate problem with money in a bank. Because you'll always set it up the same way. Percent times liters plus percent times liters equals percent times liters. Okay. And then, why can't you square root a negative number? Why can't you? Like if I had the square root of -1, why isn't there an answer? Someone like to try that one? I can tell you're thinking about it, Uriel.
Was it because back then it was like mathematicians said it was only
Yeah, exactly. There really isn't an answer. There's not a real number answer. If you type it in your calculator, it'll tell you it's an error. There is no actual real answer to it. And in fact, you could even make a little proof about it. You could say, well, let's say that the square root of -1 really was a number. Like, let's say there really is an answer. Then now I can do algebra on this. I can say, well, -1 is being square rooted, so I can square both sides and cancel that out. And now I'm looking at this and I'm saying, okay, whatever the answer is, if I square it, it should be -1. But is that possible? Can I take a number and multiply it times itself and equal a negative? No, definitely not. Because let's say the x is positive. A positive times a positive is positive, so that won't work. Let's say x is negative. A negative times a negative is still positive. That won't work. Let's say it's 0. 0 times 0 is 0. That won't work. So there's literally no number that could possibly satisfy this. So first of all, that's why you can't square root a negative number, because there's no real answer. But then why did mathematicians say we should do it anyway? Why should we just go ahead and square root a negative anyway and call it something? Yeah, to finish the problem. Exactly right. So let's say that they had a simple equation like x squared plus 1 equals 0. It's an equation. You know, mathematicians want every equation that you write down to have an answer. So if somebody wrote down the equation x squared plus 1 equals 0, you would go about doing your typical algebra, and you'd say x squared equals -1, square root both sides. And you'd look at that and you'd say, well, apparently the answer is the square root of -1. And I realize I can't do that on my calculator, and it has no real meaning. Well, let's just go ahead and give it meaning anyway, and we'll just call it I. And then that way, we can just kind of lump all the equations in the world that end up with answers like this, and we'll just call all those equations essentially imaginary. So mathematicians didn't want that to be the end of the game, so they said, let's just call it I and keep going. Okay, well, folks, thanks. Those are our little conceptual warm-up questions. Let's go ahead and keep going. Today is what? January 24th? So we're going to finish section 1 through 1-4 today. Sorry, that's a typo. The midway isn't, the quiz isn't due today. I didn't even give it to you yet. I'll give you the quiz today after class. It's a hard copy. You'll take it home. You'll write out your answers on the sheet and then bring it back next class. So this kind of worked out nicely for you guys that I pushed it back a day because now you have the whole weekend. You can go home, look through your notes, look through the book, and finish your quiz and bring it back. Okay, a couple notes. Well, just one note. Folks, I would say maybe 10 of you still haven't signed up for my math lab. Unless those 10 of you did it between yesterday and today, then great. But I think there's still quite a few of you who haven't signed up for my math lab. I would encourage you to do it today. Like, not literally right now because we're in class, but right after class is over, go online and sign up for my math lab. Again, if you're still waiting on financial aid or anything like that, you can sign up for a free account for 2 weeks. That gives you 2 weeks before you actually have to pay. But definitely sign up for it today because we've already covered some material. And I think you could, it would be a good idea to do your homework immediately after class. So everyone, sign up for my math lab today. All right, now I have a joke for you. We already did the 30 cows joke, right? Did anyone go home and tell that to your friends and family? Yes. Oh, all of you did. Okay, fantastic. Well, I have a new joke for you today. This is more of a classic joke. When did the man go to the dentist? Say it again, Raheem. Did you guys hear it? Tooth hurty. Tooth hurty. Yeah? All right. Well, I like cute little puns like that. That's the type of joke I'll be telling. All right. So here we go, folks. We're starting up in section 1.3. We had just finished last class doing a little interlude in which I kind of described imaginary numbers and why we use them. But now we're right back into our notes packet. First of all, I just want to confirm, does everybody have it? Everybody has the notes and it's open notes section 1.3. And Jake, you have yours too? Okay, super. All right, so now that we're a little familiar with imaginary numbers, we can go ahead and compute these. So recall the product rule for roots. First of all, go ahead and write the rule up there. The product rule states that the square root of m times n is equal to the square root of m times the square root of n. That's called the product rule for roots. It means you can break a root up over multiplication. Did we already say that you can't do that over addition? We did? Okay, yeah. So it doesn't work for addition, just multiplication. So write the number as a product. So the square root of 25, that's simple. It's just 5. But what about the square root of 75? How do we simplify this? Go ahead, Eric.
The square root of 25 times 3.
Yeah, that would be 25 times 3. So I just take the number inside the root and I cleverly rewrite it so that it's a square number times a non-square number. And then I can break that root apart into root 25 times root 3. And then I can actually simplify the first part. And that's why you try to take a number and break it apart into a square times a non-square. Because that way you can simplify the first part. All right, so now how about the square root of negative 49? First of all, if you type that into your calculator, what will it say? Error. But we know that we can do it anyway. How do we split this one apart? Well, that's true. You could go ahead and split it apart all the way down to 7 times 7 times negative 1. I'm just going to split it apart into 49 times negative 1. Because that way I'm splitting it apart between the real part and the imaginary part. So then I have the root 49 times the root of negative 1. And I can go ahead and calculate the normal square root of 7. And then I just put an I next to it. So the answer is 7i. Now, over time, you'll just get so used to that if you see a problem like the square root of negative 36, you would just automatically think to yourself, oh, the square root of 36 is 6, and it's the square root of a negative, so you would just write down 6i. And that would be okay. Like, that'd be an acceptable amount of work if you just went straight from here to here. But if it still feels more comfortable to break it apart right now, then I suggest you do that. All right, what about the square root of negative 50? How do you break that one apart? Michael, how would I break apart root negative 50?
You do like I do with the 75 times 25 times 2.
Yep, so you'd have 25 times 2 times?
Oh, I?
Yeah, well, not I yet, but yeah, the negative part. Yep. So that way you'd have the root 25, then you'd have the root 2, and then you'd have the root negative 1, And then you can go about simplifying all of that. So we would end up with what? 5 root 2i. Did we say what the rule is for where to put the I? You have to put it before the root. And why do you have to put it before the root? Yeah, to avoid confusion. You don't want someone thinking that you're square rooting the I. That'd be a little scary. What's the square root of I? That's even more complex. So instead, you'd want to put 5i root 2. And that way there's no confusion about square rooting the I. All right, so folks, we will be dealing with expressions that look like this. 8 minus the square root of negative 20 all over 2. What does this expression, where did this expression come from? Do you recognize the form of that expression? Where do you think that expression came from? Yeah, it came from the quadratic formula. So you might as well go ahead and jot it down just to remind yourself. The quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. So now looking at that, it makes it a little more obvious where that expression came from. It's not just some arbitrary random thing that someone wrote down. That is the result of someone doing the quadratic formula. So the question is, once you do the quadratic formula, can you simplify that expression further? Can we simplify that expression further? Yeah, we can. How could we, Gabby? What about it can simplify? Yeah, maybe you're tempted to simplify the 8 and the 2. You're like, hey, 2 goes into 8 and 2. I want to cross those out. But you can't do just the 8 and 2. Whenever you simplify top with bottom, the 2 would have to simplify with both objects up there. So how can we simplify the root negative 20? Yeah, we'd have to break down 20, right? So I'm going to go ahead and do a little scratch work. I'm going to do my breakdown of negative 20. Who'd like to break that one down for me? David? How would I break down 20 into a square number and a non-square number? What square number goes in?
5 and 4.
Yeah, 5 and 4. So that would be 4 times 5 times negative 1. So that's root 4, root 5, root negative 1. So that gives me 2i root 5. So now I have my 8 minus 2i root 5 all over 2. Now I can legitimately cancel the 8 and the 2 with the 2. No, how does that work? Why am I allowed to just cancel the 8, the 2, and the 2? Not cancel, but divide them all by 2. Yeah, because they all can be divided by 2. And there's 2 different ways that you can think about that. You could either break this apart into 2 separate fractions. You could call this 8 over 2 minus 2i root 5 over 2. That's one thing you're allowed to do. You can break up a fraction with multiple terms in the numerator and take each term in the numerator, put it over the denominator separately, and create 2 separate fractions. That's one thing you're allowed to do. And now it's obvious. These 2's cancel out, and this 2 goes into 8 4 times, and so our answer is 4 minus I root 5. What do you think? How does that answer look? Looks pretty good. It looks much better than the original answer. It looks much better than the original answer, which is why we are compelled as mathematicians to simplify whenever we can, because it makes it look better and the numbers are smaller. Okay, now this next question, I actually had a question just like this pop up on my Facebook feed the other day. Now I realize that's probably because I'm a geek. I don't know if it pops up on everybody's Facebook feed, but it was advertising to me this service called Brilliant Puzzles, and they send you puzzles every day. So they said, most people won't get the answer to this question. So how do you think most people would approach this question? Since, you what? Yeah, they're probably just multiplying. We can do the product rule in reverse, right? If you did the product rule in reverse, this is the wrong way. Don't write this down. But if I just multiplied them together to form one root, it'd be negative 5 times negative 5 on the inside. Is that fair? I mean, so far that seems logical that I could merge the 2 roots together, which is true from the product rule. And then that would give me what's negative 5 times negative 5? Positive 25, and then the square root of positive 25 is 5. But unfortunately, that's not correct when it comes to imaginary numbers. We have to be very careful. If you're given an imaginary number, that number is imaginary, right? And so you have to treat it as such. So what you really have to do, okay, now this is the right way, everyone write this down. What you really need to do is turn root of negative 5 into root 5i. You have to pull the I out. So that's really I root 5. Maybe I did that too fast. I should show my work. The square root of negative 5 is actually the square root of 5 times the square root of negative 1, which is really the square root of 5 times I. So that's very important. That's actually I root 5. That's I root 5. And now how do I multiply? Yeah, so you'd have I times I, multiply like with like. I times I is I squared. And then root 5 times root 5 is root 5 squared. And what happens when you square a root? They cancel out, and so that's just 5. And what's I squared? Negative 1. I squared is negative 1. And so now our answer is actually negative 5. Isn't that crazy? The real answer should be negative 5. Even though it really looks like this first thing should have worked. But the first technique does not really treat them as imaginary numbers. It kind of allowed that imaginariness to just vanish by multiplying a negative times a negative. So the rule for imaginary numbers then, folks, is you always have to pull out the I first things first. Pull out the I before you start doing any sort of computation. Does that make sense? Pull out the I? What I'm saying, pull out the I, yeah. All right, so how about this one then? Could we just go ahead and say, this is the wrong way, don't write it down. Could I just do the square root of negative 18 over negative 2? And then a negative over negative is positive, so I'd call that 18 over 2. And then I'd say, well, that's the square root of 9, which is 3. Is that correct? That's not correct, because I didn't give due respect to the imaginary component. So what do I have to do first, actually? Yeah, we have to pull out the I from both of those. That's really I root 18 over I root negative 2. I'm sorry. It's really I root 18 over I root 2. You have to deal with the I first. Then we could go ahead and, well, I guess this is kind of funny. The answer turns out to be the same. What happens to the I's? Since there's one on top and one on bottom. They actually do cancel in this case. So your I's cancel. You end up with root 18 over root 2. In which case, you could still call that root 18 over 2. Now, what did I just do here? I went from root over root to one big root. Am I allowed to do that? I am allowed to do it, and it's another example of the product rule. The product rule can also be written like this. It can be that the square root of a fraction is equal to the square root of the top over the square root of the bottom. So that is a legitimate thing. You can also break up a root over division. You can break a root over multiplication. You can break a root over division. Okay, so now we have the square root of 9, which is 3. So you might say, well, Mr. G, so in that case, can't I just do it the first way? Since it's the same. And I'd say, no, let's just always be careful and pull out the I as soon as you see it. All right. Now, I think we already talked about this. How do you combine like terms with I? What's that, Michael? Yeah, just the normal way. You just treat I like a normal variable. So this is just, first of all, that's a minus, so I have to remember to distribute that. But it would just be 8 plus 9i, and then minus negative 6, which is really plus 6, and then minus I, which is just minus I. So the first thing I did was just distribute. But then at this point, you just combine like terms as if I is any other variable. So what did we get? Garrett, what did you get? Yeah, once you combine like terms.
8i plus 14.
Yeah, 8i plus 14. Can we do anything else to that? No, that's it. That's just simplified. That's just simplified. All right. So this is just a lot of mechanics about how to deal with imaginary numbers. In and of itself, this isn't very interesting. It's just how to deal with computations when there's an imaginary number involved. Now we can start to talk, well, okay, there's a couple more I problems, but then we'll start putting this in context and seeing why we actually do all this. All right, so how do you square a binomial? Yeah, that's just the definition. Who said that? Oh, thank you, Garrett. Yeah, whenever you square a binomial, you have to multiply it by itself. That's the definition. So we would all go ahead and write down 8 minus 5i times 8 minus 5i. And then at that point, you just do normal FOIL. So you do your first, outer, inner, last. I'm always going to draw my lines. First is 64. Outer is minus 40i. Inner is another minus 40i. And then last, this one's a little tricky. What's negative 5i times negative 5i? Miranda? What would negative 5i times negative 5i be? Yeah, plus 25i squared. Now, I know you know that I squared is equal to negative 1, but maybe just write down I squared first. There's no need to try to immediately say, okay, well, I squared is negative 1, so I'm going to write minus 25. Just write it down so you have your work, and then you can say 64 minus 80i, and now you know that since I squared is equal to negative 1, you're really subtracting the 25. I really encourage you to go slow and show as much work as possible. Even though you probably could have done some of that in your head, you'll just get in I think you could get in an accident if you're just automatically trying to do all that in your head. So, last step, 64 minus 25 is what? Is it 39?
Yes.
Oh, great.
Yeah.
All right, great. So that's our final answer. Now, folks, one of the most common mistakes people make, what do you think is the most common mistake people make when they see the problem 8 minus 5i squared? What do you think they accidentally do in their hasty enthusiasm?
Just square the numbers inside.
Yeah, just square both numbers, right? They might just accidentally write 64 plus 25i squared. And then they would get 64 minus 25, and then they would get 39. So what's wrong with that? What's wrong with that? I mean, the first thing you could say is it's wrong. You can say, well, they didn't get the full answer. What part of the answer didn't they get? Yeah, they didn't get the imaginary part. In fact, they got 64 and they got 25i squared. What didn't they get? They didn't get either middle term, did they? So if you just square both terms, they didn't do FOIL. What did they do? They skipped the OE. They completely skipped the OE. All they did was flip. So you can't just square both terms. All right. Now, here's one more question. It's kind of cute and clever. How do you simplify I to the power of 30th? I to the power of 30. Now, what's one thing you could do?
Divide it.
Would you what? Well, that is correct. You do take the 30 and you divide by 4 and you look to see what the remainder is. But before you do that, what could you do? You can just type it in your calculator. And if you type it into your calculator, provided you have a good graphing calculator that's high enough, I think you need a TI-83 or TI-84 or above. You could just do that and it would give you the answer. So how do we do it by hand? Gabby just suggested the answer, but I'd like us all to understand why. Let's go ahead and do the first couple powers of I, folks. So first of all, if we just start with I to the first power, that's just I, right? So I to the first power is I. That's just an obvious statement of truth. So what's I squared? Negative 1. So what's I cubed? What's I cubed? Now right then you might be like, oh no, I'm not sure, that looks crazy. But we could always baby step it and say, well, whatever I cubed is, it's got to be I times I times I. And I already know what I times I is. I squared is negative 1. And so I can say negative 1 times I, and therefore the answer is negative I. So you can always baby step your way to the answer by just breaking it down. So then what would I to the fourth be? How did you get 1? Yeah, because I squared is negative 1, and I've got 2 I squareds in there, right? So I to the fourth is really I squared times I squared, and since I know that I squared is negative 1 and I squared is negative 1, that gives me 1. So I now have 4 parts. Well, I now have 4 powers of I, and I'm going to write it down more simply. So I to the first is I squared is negative 1, I cubed is negative I, and I to the fourth is 1. So what's I to the fifth? Yeah, it is I, but how would you demonstrate that to someone so they believe you? How can I rewrite I to the fifth? You could do I squared I, right? That'd be fair. You could do I squared I. But what else could you do that's even simpler? You could do I times I times I times I. What about I to the fourth times I? Because what's I to the fourth? 1. So that would be the fastest and simplest way, would be whenever you have a large power of I, start chunking it down in powers of I to the fourth. Because all those I to the fourths are simply 1 and they'll just cancel out. So look again at I to the 30th. What's I to the 30th? I to the fourth times 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 I to the fourth. How many? 4, 8, 12, 16, 20, 24, 28. There. Did I do that properly? So I to the 30th is really all those I to the fourth times I squared. And what do all those I to the fourths equal? 1. Well, just 1. And so what do I end up with? Just I squared. So I to the 30th is equal to I squared. Now, let's just say that you don't have the patience to write out all those I to the fourths, right? Then what Gabby suggested is you just take any power, you divide it, well, whatever power they give you, divide by 4, and you look at the remainder. So 4 goes into 30, 7 times 4 is 28, and the remainder is 2. So whatever the remainder happens to be, that's what your answer is. Now, is the answer really I squared? What's I squared? -1. Okay, so -1 would be the answer. All right. Now, I think that's all the fancy fun we're going to have with I. Now, just as a challenge, I won't give you the answer right now, but anybody who wants to go try to look it up, what is the square root of I? That's a challenging question. In fact, it is a very challenging question. I don't think that, we don't cover the material in this class to answer that question, but maybe you want to look it up because it's a really interesting answer. Okay, so I'm just throwing that out there for you. Let's keep going. All right, there is one more thing we get to do with I, and that is what if I happens to be in the denominator? Is that a problem, I being in the denominator? I don't know if you've already covered this in a previous class. Is it okay to leave I in the denominator? It's not. Maybe you know that just by the way I'm asking the question. I'm leading you into it. You're not supposed to leave any square root in the denominator, in fact. So the idea is that rationalizing the denominator means don't leave any roots in the denominator. All right, it's a mathematical party foul. So a mathematical party foul, for instance, let's say you roll up to a math party and everybody's hanging out talking about math, and you happen to say, hey guys, guess what? Last night I ate 12/24ths of a pizza. Would that be acceptable for you to tell people that you ate 12/24ths of a pizza? What should you tell people? I ate half of a pizza, right? Nobody's going to like you if you go around saying unsimplified fractions because it's unnecessarily complex, right? You don't do that. And so one rule in math parties is you always simplify fractions, and we all know that. Well, another rule is that you never leave a fraction with a square root in the denominator. Like if you walked up to somebody and said, oh, the answer is 5/√2, they would say, whoa, you're not allowed to have a square root in the denominator. Because you'd have to go about simplifying it. So as a review, how do you get rid of a square root in the denominator? If you don't want that root in the denominator, what do? Yeah, multiply what? Top and bottom by the √2. Exactly right. This is called rationalizing the denominator because now in the top I have 5 times √2, and on the bottom, what's √2 times √2? Just 2. Right? The square root of 2 times the square root of 2 is just 2. And in case you'd like to see a proof of that, √2 times √2 is really √2 squared, and squaring and square rooting cancel out, and the answer is 2. All right, so this is called rationalizing the denominator. So does this expression, 9/-I, is there a square root down there? What is I? The square root of -1. So in fact, I is a square root, and you're not allowed to leave it down there. So everyone, let's write this down together. And in fact, I'm just going to go ahead and bump that negative sign up to the numerator. Am I allowed to do that? Can I just put the negative sign in the numerator? Yeah, the negative can be on the top or the bottom. So I'm not allowed to keep my I in the denominator because I is technically a square root. So how do I get rid of I? It's going to be the same process. Since there was a root 2 in the bottom, we multiply top and bottom by root 2. What should I multiply top and bottom by? I itself. If I just multiply both the top and the bottom by I, then in the numerator I have negative 9I, but in the denominator, what's I times I? I squared, which is simply negative 1. So now I have negative 9I over negative 1. The negatives cancel out, and in fact the 1 is in the denominator, so the answer is just 9I. Now wouldn't you agree that looks better? You know, compare the original, 9 over negative I. Ew, that doesn't look very good. Compared to 9I. It's just straightforward, there's no fraction involved. So that's why we would say that's simplified, and that's how you simplify it. Now how about this expression? Are we allowed to have the I in the numerator? Yeah, that's fine. Are you allowed to have the I in the denominator? No. So how do we get rid of this I in the denominator? We have 4 plus 2I over 7 minus 9I. What do I have to do now? This one's not quite as straightforward. You can't just multiply the top and bottom by I. What do you have to multiply by? 7 minus 9I?
7 plus 9.
7 plus 9I? Which one will work? We could try them both, right? We could always just try lots of things to see how can we get rid of the I. I'm going to go ahead and have us try the correct thing so we can all see it work out. We're going to multiply times 7 plus 9I. Now, why 7 plus 9I? First of all, what's the name for that? When you have two binomials that are only different from the fact that one is a plus and one is a minus. What do you call that? When you have the same numbers, but one's a plus and one's a minus. Yeah, conjugates. This is called a conjugate. And the beauty of a conjugate is that when you do FOIL, well, let's just see what happens. When you do FOIL, what happens? We'll go ahead and do the FOIL on the denominator, folks. So 7 minus 9I times 7 plus 9I. First, 49. Outer, plus 63I. Inner, minus 63I. And last, minus 81I squared. What happens when you FOIL conjugates? Nancy? No? What happens when you FOIL conjugates? Allison? Yeah, the middle terms cancel out. The middle terms cancel out. Once again, in the act of FOIL, when you multiply conjugates, the OI cancels out. But this time in a good way. This time you wanted the OI to cancel out. By multiplying out conjugates, it cancels the middle term, and that way the denominator is 49, and then that's an I squared, which is negative, so negative 81 is plus. Now the denominator is 49 plus 81. And we did it. We canceled out, we no longer have an I in the denominator. And that's what we wanted. So what is my final denominator? Does someone already add that? 130? Okay. So we can all feel a sense of accomplishment. There's no longer an I in the denominator. It's just a real number. Are we done with the problem? Well, no, geez, we still have to do the whole numerator, right? The whole numerator still needs to be computed. In the numerator, are those conjugates? No. Will the i's cancel out? No. So we're still going to have an imaginary number in the numerator. But at least we don't have it in the denominator. So now, FOIL the numerator, folks. Go ahead, everybody, FOIL the numerator. And we'll compare answers and see what we get. Folks, your steps and your work look really good. I can tell you're all professionals. Have I called you professionals already? I don't know if I have, but really, your work looks great. So let's see here. First, 28, outer, 36i, inner, 14i, last, 18i squared. And so our I terms do combine. into 50i. And then 28 minus 18. Yeah, 28 minus 18 is 10. Did anyone else get 10 plus 50i? Did you guys? Oh, good. Okay. Now, does that automatically mean that we're right just because a bunch of us got the answer? I mean, maybe we're all making the same mistake. I don't know. How can we check? How do we check to see that we got this right? Well, plugging it in normally would work, but we don't have an equation to plug it in to see if it's true or false. So right now, what can we do to see if it's right? You can just check in the back, right? What does the answer in the back say? We should all look, because the answer in the back is going to be a little more specific. What? Yeah, they broke it down into fractions, didn't they? They're going to break it apart into two different fractions, just like we did a second ago. So it's really going to be 10 over 130 plus 50i over 130, which further simplifies into 1/13 plus 5i 13ths. Is that the answer in the back? Is it? Yeah, okay. So that's what your final answer would look like. I share that just in case on my math lab they want that answer as opposed to that answer. But what do you think? What answer looks better? Do you like 10 plus 50i over 130, or do you like 1/13 plus 5/13i? Which one do you like?
I mean, I had a person. You just do 1 plus 5i.
1 plus 5i. Oh, yeah, you could also say 1 plus 5i over 13. That's fine too, Michael. Thanks for asking, because this is just them merged together as one fraction, and that's split apart into two fractions. Yeah, you could totally do that. Great question. All right. Well, folks, we're ready to start section 1.4, which is all about quadratics. And so I'd like us to start by just thinking about what a quadratic is, and what the graph of a quadratic looks like, and what the details are when we study a quadratic. So let's start with the etymology. Wait, let's see here. Can I put this here? Yeah, that much better. Okay, my essential question for you is, what does it mean to solve a quadratic? What does that mean, to solve a quadratic? And as an example, I gave you 3 different quadratic functions. I gave you x squared minus 3x minus 4 equals 0, x squared minus 2x plus 1 equals 0, and x squared minus 2x plus 10 equals 0. So what does it mean when you solve a quadratic? This is a really important, good question. Let's start maybe by saying what a quadratic is. Does anyone know the etymology of quadratic? We've already talked about etymologies, right? Yeah. So what's the etymology of quadratic? Does anyone want to take a guess? Look at the word quadratic. If you were just to take a guess, what do you think the root word is? Quadra, right? And I heard a lot of you already guessed 4. Why are you saying 4? Why do you think quadra means 4? Because the word quad, that's true. Maybe you ride like ATVs or quads. Why do they call those quads? Because it's a 4-wheeler? Yeah. What other word do you know that starts with quad? A quadrilateral. Quadrilaterals have 4 sides. That's true. So surprisingly enough, the word quad is associated with the number 4, but it's not the actual etymology of the word quadra. Does anyone want to take a guess about what quadra really means? It actually means square. If you go back to the original Latin, it means square. Now, what about a square has the number 4 in it? The fact that there's 4 sides, right? But technically speaking, quadra means square. So now we can answer the question, what about this formula, ax squared plus bx plus c? What about that formula is evocative of a square? Where's the square? The what? Yeah, the exponent on the x. That's what makes it quadratic. So we call this thing a quadratic function because of the fact that it has an x squared term, and square, the root word for square is quadra. So we call this quadratic because they're talking about the fact that there's an x squared. If I take away the x squared term, what am I left with? bx plus c. You might not recognize bx plus c, but how do you normally see that written? Instead of bx plus c, you'd normally see mx plus b, right? mx plus b is a linear function. If you had mx plus b, that would just be a straight linear function. But as soon as you add the ax squared term, that changes a line into a parabola. So it's really this term right here that makes a parabola, and that's why they call it a quadratic function, because of the fact that there's an x squared term. So that's just a little etymological history there for you, so that the next math party you're at, you can wow your friends, be like, well, actually, quadra means square. Okay, so then what does it mean to solve it then? How would you solve ax squared plus bx plus c? What formula? The quadratic formula, right? So again, I'm just going to write it down. The quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. What does that formula tell you? What does the formula tell you? You know, like let's say you finish doing the formula and you get x equals 4 and let's say, actually, yeah, 4 and negative 1. Let's just say. Let's say you did the formula and those are the two numbers that popped out. What are those two numbers? They're the what? Yeah, they're the x-intercepts. I heard someone else say they're the zeros. Both of those are the correct answers. When you solve the quadratic formula, what you're actually doing is finding the x-intercepts of your quadratic. So for instance, you might not be able to tell just from looking at this parabola here, but it is actually the graph of x squared minus 3x minus 4. And there's no scale up here, so you can't see it. But I'll go ahead and tell you, the x-intercepts are negative 1 and 4. So for that particular function right here, if you did the quadratic formula, you'd get the numbers negative 1 and 4, and those are the x-intercepts. So the first question is, what does it mean to solve a quadratic? It means to find the x-intercepts. That's really important. So first, we're finding x-intercepts. And that is what the quadratic formula is telling you, is the x-intercepts of a quadratic. Now, what can you do with those two numbers? What can you do with the numbers negative 1 and 4? What can you do with them? Plug them in. Thank you, Michael. You can plug them in. What would happen if I plug them in? It should equal 0. Exactly right. So I'm going to do 4 first because it's easier. 4 squared is 16 minus 3 times 4 is 12 minus 4 is 16 minus 12 minus 4 equals 0. Yeah, so that's what you can do with x-intercepts. X-intercepts, whenever you plug them into the original, it actually makes a true statement. So will negative 1 work as well? What's negative 1 squared? Just 1. And then negative 3 times negative 1 is plus 4. And then, uh-oh. Did I write down the wrong x-intercept? That would be a 1. Oh, I wrote that down wrong. Yeah, thank you. That's plus 3. There we go. Yeah, negative 1 squared is 1. Negative 3 times negative 1 is plus 3. And then minus 4. And sure enough, 1 plus 3 is 4. Minus 4 is 0. Okay, so that's what these two numbers do. Negative 1 and 4, they are the x-intercepts, but they also make the equation equal 0. All right. So that's our big conceptual question for what we're doing over the whole rest of this class period and the next couple days. What does it mean to solve a quadratic? To find the x-intercepts, which make the equation equal 0. Actually, I can say that better. Which make the equation true. Which make the equation true. So could I have all of you say that with me? Okay, because really, truly, I want this vocabulary in your mouth so that you could say it to somebody who asked. If somebody said, what does it mean to solve a quadratic? You would say, to find the x-intercepts, which make the equation true. So in two parts, everybody. What does it mean to solve a quadratic? To find the x-intercepts. To find the x-intercepts, which makes the equation true. Which makes the equation true. Now say the whole thing. What does it mean to solve a quadratic? To find the x-intercepts, which makes the equation true. This is one of the most important concepts when you talk about studying quadratics. Now, all that said, how many solutions does this quadratic have? How many solutions does it have? 2, right? Because it has 2 x-intercepts. How many solutions does this one have? It is just 1. There is just 1 solution, right? Because the quadratic is just barely touching the x-axis. It only touches it in 1 spot. So there is actually only 1 number that I can plug in here. It is sometimes called a double root because if you do, if you actually factor, well, I don't want to get too far ahead of myself. There's 1 solution, right? There's 1 unique solution. How many solutions does this have? None would be a good guess, right? Does it touch the x-axis? Are there any x-intercepts? So there's no solutions. But the fact is, there are no real solutions. There are no real solutions. What kind of solutions do you think there are? Imaginary. Yeah, this one has imaginary solutions. When you do the quadratic formula on this, you end up with some sort of like a 2 plus or minus the square root of 5, negative 5, when you do the quadratic formula. Oh, I meant that to be 5. Yeah, there we go. When you have a parabola that's floating above the axis, the solutions do exist because you can always do the quadratic formula on anything. But it's going to end up with a negative under the square root, which makes it imaginary. So when there are no x-intercepts, there are still solutions. It's just that the solutions are imaginary. Whereas if the parabola actually touches the x-axis or cuts through it, the solutions are real, and you actually have real solutions. All right, folks, that's the concept behind what we're about to do. That's what we'll be thinking about as we solve these next few problems. So let's go ahead and do it. Section 1.4, solve the equation by the square root property. Okay. So folks, we have an equation, and right now we're trying to solve for x, right? But we're really looking for the number you can plug in to make the equation true. So what number can we plug into the equation to make it true? That's what we want to find. So how do I solve this problem? It says to solve it by the square root property. What's the square root property? What do you think? Yeah, you could just square root both sides and cancel out the square. And that's exactly the square root property. It just states that if you have something being squared on one side of the equation, you can go ahead and square root both sides, and then that'll cancel out your square, and you end up with 7x plus 4 equals the square root of 4. Now, big question. What's the square root of 4? 2, right? Obviously 2. But there's another answer. Yeah, plus or minus 2. Anytime you do a square root as an action step in an algebra problem, you have to account for the fact that it's really plus or minus. Okay, so you might want to make a note. Anytime you're doing algebra and you do the action step of square rooting both sides, that's when you have to make the answer plus or minus. All right, normally if I just walked up to you on the street and I said, what's the square root of 15? Oh, it's not about 16. If I just said the square root of 16, you could just say the answer is 4. Because normally we just want the positive square root. But if it's in an algebra problem and you square root both sides, that's when you have to write plus or minus. Okay, so continue on. X is being multiplied by 7 and adding by 4. Now, folks, I really hope you all write this down the way I write it down. So I'm going to add minus 4 from both sides. And at this point, it's very important that you write the negative 4 first and the plus or minus 2 second. As opposed to writing plus or minus 2 minus 4. Why do I want you to write it down in that order? Is it just because I'm very persnickety and needy? Well, yeah, we are eventually going to need it to solve it both ways. That's true. Why else would we want it to be in that order? So not to confuse the signs, that's also very important, yeah. And why else would we want it in that order? So that it looks like the quadratic formula. We want our answer to look in form like the quadratic formula. And what's essentially the form of the quadratic formula? It's a number plus or minus another number all over a number. That's what the quadratic formula essentially is. It's a number plus or minus another number all over another number. So we want to keep, as we solve for x in quadratics, we want to make the form of our answer look like the form of the quadratic formula. Okay, so now let's keep going. I divide both sides by 7, and voila, I have negative 4 plus or minus 2 all over 7. Does that look like the form of the quadratic formula? Yeah, that's what we want. Now let's see here. Who said it? Did you say about doing 2 cases? What was her name again? What is it? Lori. Okay, thanks, Lori. Yeah, we need to do 2 cases. Gloria, sorry, I didn't really hear you. Gloria. So Gloria, and everybody, the way I traditionally do this, I'll show 2 different arrows. Okay, I'm going to show 2 different alternate realities. I'm going to say, okay, on the one hand, it could be negative 4 plus 2 all over 7, or it could be negative 4 minus 2 all over 7. Those are the 2 different alternate realities that we're talking about. And so, on the one hand, I've got negative 2 7s, and on the other hand, I've got negative 6 7s. Now, hearkening back to that picture we just looked at, what are those two numbers? What is negative 2 sevenths and negative 6 sevenths? They're what?
The x-intercept.
They're the x-intercepts. Exactly right, folks. If I were to now take that equation and graph it as a parabola, I would have one x-intercept at negative 2 sevenths. I would have another x-intercept at negative 6 sevenths. And then I would put a little dot there and a little dot there. And do you see the parabola? Can you kind of see it in your mind's eye? There's my parabola. So that's what those numbers are. I always want to come back to this. When you finish a quadratic problem and you get your two answers, it would be nice if you made a little sketch. Just make a little quick little sketch. Say, hey, by the way, these two numbers, those are the x-intercepts of that parabola. And what will those two numbers do if I plug it back in? They make the equation true. So these two numbers are the x-intercepts which make the equation true. All right. So how do we solve this one? Same thing, right? It's under the same set of instructions. What's going to happen this time, though? Yeah, we're going to end up with this imaginary number, right? Everyone, let's go ahead and do it. So we square root both sides, and we have now this time x plus 1 equals the square root of negative 3. What will I do to the square root of negative 3 real quick? You're going to pull the I out. So now I have I root 3. And that's just fine. And what do I have to do? Plus or minus. Yeah, let's go plus or minus. Okay, so x is being added by 1, I subtract 1, and x equals negative 1 plus or minus I root 3. Does that have the form of the quadratic formula? Like, would you buy it that somebody actually just solved that by plugging it into the quadratic formula and that's the answer? Yeah, because it's of the form. It's got a number plus or minus another number, which happens to be a square root. And then there's no over 2a. So theoretically, that canceled out somehow, right? Either the 2a became the number 1, and there was no denominator, or something canceled out. Okay. Now, what are our two different numbers? Our two different alternate realities. We have negative 1 plus I root 3, and we have negative 1 minus I root 3. Those are our two different solutions. Now, what are those numbers? They're imaginary, but what do they represent? They what? Well, that's true. There's no real solutions. What do they represent, though? They do represent x-intercepts. Now, are they actually x-intercepts? What graph are we looking at? Yeah, we're looking at the third one where it's floating above the axis. So the fact is, I can't actually put those two x-intercepts on the x-axis because the x-intercepts are imaginary. So what will I draw? This is just a rough sketch. What would I draw? I just draw a parabola floating above the x-axis. That's it. And anybody who's a mathematician would say, oh yeah, sure, man, I get you. The parabola's floating above the axis. I know what you're saying. And that's this is a really good graph of this parabola, believe it or not. That's a great graph. Now probably, we could figure out where it is left and right, where it is up or down. But the fact is, the parabola is floating above the x-axis. And that's what it tells us by the fact that the roots are imaginary. All right. So that is solving by the square root property. I believe we're about to review 4 different techniques. I suppose I could leave that up there. We're about to do 4 different techniques, I think. The first technique is the square root property, which just means that you square root both sides. What do you think our next technique is going to be? If you already turned the page, you already know. What's our next technique for solving a quadratic? Yeah, zero factor property, which really means what are we about to do? We're not going to do the quadratic equation just yet. But kind of the classic thing that you did throughout lots of Math 120 is you danced. No. You factored. Our next technique is to factor. So I'm just going to write that down first. Our next technique that we're about to review is factoring. But we'll go ahead and take a break. So the time is now 9 o'clock. So everyone please be back in the room by 9:09. Thank you. Yeah, we're just finishing my recording. Wow, this is very doable.
Hey, Mr. G.
Hey, Julian.
So 8:01 is late.
Well, you know, I was gonna talk to. I saw a couple of you guys come in the room today. We're right at 8:01, and I'm like, ooh, boy, that burns. I bet they both want to come ask me, like, oh man, is that late? And yes, technically it is late. Now, Julie and I have immense empathy and sympathy for you because you're like, oh man, I was like right here, and had you even just maybe walked a little quicker,
Yeah.
you know, anything like that. So I think what I might do, Julian, is first I need to double check who was just. Was Julian? Yeah, I saw maybe 2 or 3 of you walk in like right at 8:01.
Yeah.
So what do you think is the right thing to do for me in terms of my sympathy for you?
Well, or not take off a percent.
Right. Well, I'm not going to do it yet because you get 2 free tardies.
Yeah. Well, I was late.
Oh,
Yeah.
okay. Well then, Julian, this is an important conversation for us to have. If you've already been late these last 2 classes, what's going to stop you from being late for all the next few classes? Like, tell me, what can you do to control your behavior so that you will be on time next time?
Start early.
Yeah, you just have to start earlier. So believe it or not, Julian, I want to have sympathy and compassion for you and not take up any percentage points. But the fact is, right now, you have already demonstrated a pattern of being late. And that's exactly why I have this really strict policy, is to kind of give you a spiritual kick. Be like, all right, man, you gotta start getting here earlier.
Yeah, because when I parked, I was like, I'm here on time.
Yeah. So I tell you what, obviously I don't want to take percentage points off of anybody. Julian, I don't want to do it to anybody. I don't want to do it to anybody. And the fact is, I'm not doing it to you. You need to be here on time.
Yeah.
Okay, so what I would consider, Julian, if I, because I have to be fair to everybody, I can say like, everybody, you can have a grace period because it's the first couple of weeks.
Yeah.
But at the same time, I already gave everyone a grace period by saying you can have 2 free weeks.
True. Yeah.
Yeah. So then where do I draw the line? If I keep on giving grace, then ultimately everybody might just keep on being late. So can I think about it?
Yeah.
All right. Let me just think about it. But what are you going to do on Monday?
You're gonna start early.
Yeah. And you know what I would probably be? With it early. Right? Like, you probably want to be 10 minutes early.
Yeah. Well, right now, like my work schedule, I'm probably gonna change it, but I literally get off at 6:30.
Oh, you do in the morning?
Yeah.
Oh my goodness. So then what do you do? Like, you go home?
Yeah, I
You
rush
shower,
home
change.
and then rush here.
Oh my gosh. Okay. So,
Yeah, I'm actually gonna change my work schedule.
wow. So you work all day long?
Since 11 p.m.
Wow. So then what after class do you go home and go to bed?
Yeah.
Wow. That's a very unique work schedule.
Yeah, but I'm changing.
All right. For just a couple months in my life during college, I was nocturnal. Like, I would be up all night long and would sleep during the day.
Yeah.
All right. Well, yeah. My big message is that I would recommend you start getting here as early as you can. Like at least 10 minutes. That way you have a buffer. Because what's the worst that happens if you're early? Nothing. You can just sit, you can feel ready.
Not be late.
Yeah, exactly. My wife and I have a joke because we are often late going places. And so we always say, God forbid we're early. Like, well, honestly, what's the worst thing about being early? Nothing. There's no downside at all. Anyway, that's the total show. Okay. Oh, oh, then I wonder. Oh, oh, okay. All right, folks. I think everybody is just about back. Yeah, there we go. All right, folks, let's keep going. So right now what we're doing is reviewing our different techniques for solving a quadratic. And again, what does solving a quadratic mean? You're finding the x-intercepts, which make the equation true. So all of these techniques that we're about to do are all about solving quadratics, which are how you find x-intercepts, which helps you draw the picture, first of all, and it makes the equation true. So the next technique is called factoring. And it says solve the equation by the zero factor property. Recall, when you factor, this is the question, so everyone look at number 23. What two numbers multiply to make the last number that add to make the middle number? Remember, that's how you factor. You say, what two numbers multiply to make the last number that add to make the middle number? So I don't recommend that you just do that off the top of your head. I realize that in the case of 18, you probably can go ahead and just do it off the top of your head. What multiplies to make 18? Can you add them to get 7? 9 minus 2? Sure, you can do that in your head. But as we do more complex problems, it's helpful to make a factor table. So you take the last number, negative 18, and you say, what number is multiplied to make 18? And you list them out systematically. You start going from 1. So you say 1, 2, 3. So it'd be 1 times 18, or 2 times 9, or 3 times 6, and 4 times nothing, and that's it. Nothing else goes into 18. You could keep counting, like, does 5 go into 18? No. Does 6 go into 18? Well, yeah, 6 does go into 18, but it goes in 3 times, which is a duplicate fact. So again, we're just done. That's my factor table right there for 18. So now looking at that, I know I need to make a product of negative 18. So that means I have to multiply a positive times a negative. So I have to find a pair of numbers, one of which is positive, one of which is negative, that'll add to make 7. So which pair of numbers and which one's positive and which one's negative? Yeah, so we're going to do the 9 and the 2, and the 9 would have to be positive, and the 2 would have to be negative. So notice that all the work for this problem is actually on the factor table. By making a factor table, that's where you do all of your work, because now you just write down the answer. X minus 2 times x plus 9. Now, I know walking around the room that some of you use the box method. I myself am not that familiar with it, but I think it goes something like this, right? And then you put in the different pieces, right? And that's fine. If you have your own technique that you use for doing factoring, whatever feels best for you, that's just fine. But I will be modeling this technique up on the board to always think about what my factor table is. Okay, so now what do I do with this? Now that we factored it, now what? Yeah, you're going to solve for x in both of them, right? And here's why. We just took this problem, x squared plus 7x equals 18, or minus 18 equals 0. And we want to know, when does it equal 0? Well, by turning it into a multiplication problem, right? So we have this binomial times this binomial. What do I know if something times something equals 0? What do you know for sure about one of those two things? If something times something equals 0, what must one of them be? 0, right? One of them has to be 0. Actually, one of them or both of them. In either scenario, if this one is 0, then the whole thing will be 0. If this one is 0, then the whole thing will be 0. And again, I use little arrows to show, okay, I'm going to go ahead and set x minus 2 equals 0. I'm going to set x plus 9 equals 0. Because these are the two scenarios in which the whole thing is going to equal 0. So I go ahead and solve for x using both of them. So x equals 2 and x equals negative 9. And those are the quote-unquote solutions. Now, as I will always ask, what are those numbers? Jose, the solutions, which are the x-intercepts. They're the x-intercepts. So now we could all make a nice little drawing of an x-intercept at 2 and an x-intercept at 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 9. And then, voila. That's what our parabola would look like. By the way, folks, I would call that the end of the problem. I would call the graph the end of the problem. Having an idea, not just that x equals 2 and x equals negative 9, but knowing what those things even mean. You know, what do those solutions mean? They're the x-intercepts. They make the equation true. Now, of course, do I know that 2 and negative 9 actually are the answers? Yeah, right now I have no idea. I could be wrong, right? I could have factored wrong. I could have made a mistake. I could have had a sign mistake. How do I know if these numbers are actually correct? Hey, right, you plug them in. You just plug them in and see if it makes the equation true. I'll just plug one of them in. I'll plug in the 2 because that's nice and easy. 2 squared is 4 plus 7 times 2 is 14 minus 18. And sure enough, 18 minus 18 is 0. So that worked. I'll even plug in the negative 9. Negative 9 squared is 81. 7 times negative 9 is negative 63 minus 18. And yeah, 81 minus 63 minus 18 is 0 as well. So yes, now I feel really good. These two numbers are correct. They make the equation true. They are the x-intercepts. That's what the parabola looks like. Okay. Well, that was a nice and simple factoring problem. This factoring problem is a little harder. How do we go about doing this factoring problem? Yeah, well, what's even before that? What do you have to do? Gabby? Yeah, put them all on one side of the equation, right? I heard a couple of you guys say it. So let's go ahead and move the 21x over. and move the negative 49 over. And so you can show all the work, minus 21x minus 21x plus 49. So it's 2x squared minus 21x plus 49. Did I do that correctly? Is that okay? All right. Can I factor this the same way I factored this? Unfortunately not. Why not? Yeah, because of that darn 2. Yeah, that 2 changes everything. I cannot right now just look and say, what do I multiply to get 49 that adds to make 21? That would not be successful because there's a 2 up front. It changes everything. So in fact, what do I need to do with the 2? Yeah, multiply it by the last number, right? So I'm going to show an arrow from the 2 to the 49, and 2 times 49 is 98. And now that is my question. What multiplies to make 98 that adds to make 21? So technically, what multiplies to make a positive 98 that adds to make a negative 21? So I am, in fact, still doing the same process. I still have to make a factor table. I still have to say what multiplies to make this number that adds to make this number. It's just that I had to multiply the first term times the last term first. Now, 98. That could be, again, I'm going to go in order of counting numbers. 1 and 98, 2 and 49, 3 and nothing, 4 and nothing, 5, nothing, 6, nothing, 7 and 14. I think that's it. I'm just doing the factor table in my head. You could use a calculator to make a factor table for you. Okay, so in order to multiply to make a positive number, it either has to be a positive times a positive or a negative times a negative. And since I want my numbers to add to make a negative, it must be that I'm going to do a negative times a negative. So which pair of numbers do I make negative negative to add to make negative 21? Yeah, the 7 and the 14. So that's my solution. It's negative 7 and negative 14. However, I can't just write down x minus 7, x minus 14. That would not be correct. Why would that not be correct? Yeah, because of the 2x squared. Again, if I just did this, foiling it would just give me x squared, not 2x squared. So you can't just do it the same way you did the other one. Instead, what do you have to do? Yeah, we're going to factor by grouping. And to do factor by grouping, you have to rewrite this middle term. So instead of minus 21x, what am I going to write? Instead of, it's going to be negative 7x plus negative 14x. You have to rewrite the negative 21 as negative 7x plus negative 14x. And folks, I would carefully do negative 7x plus negative 14x. That might feel a little funny at first. Why did I say negative 7x plus negative 14x instead of just negative 7x minus 14x? So that you can group them properly. Yeah, we need to do grouping. So now we can put in our parentheses and group the first 2 terms plus parenthesis of the second 2 terms. That's very important that we have that plus in between the 2 groupings because we're still technically adding these things together. All right, now what do we do? Do what? What do we do now? We are on our way to solving for x. That's absolutely true. Well, what do we have to do first? Yeah, factor each binomial. So from this binomial, what can I factor out? Just an x. So I have x outside of 2x minus 7. Now from this binomial, what can I factor out? A 7, not an x, definitely a 7. And what else do I have to factor out? You have to factor out the leading negative. Anytime there's in a parenthesis, if the first term has a negative on it, you have to factor the negative out to get rid of the leading negative. You want the first term to be positive. So I'm not just going to factor out a 7, I'm going to factor out a negative 7. So I bring out the negative 7, and what does that leave me with? 2x minus 7. Now, how can I check to make sure that I just did that right? I wrote down 2x minus 7, but am I right? How do I check? Yeah, just distribute it back in again and see if it works. So negative 7 times 2 is negative 14x. Negative 7 times negative 7 is positive 49. So you can always check by just distributing it back in your head. All right, now, folks, this was the magic moment. 2x minus 7, 2x minus 7, they're the same. Thank goodness. They have to be the same. Otherwise, you can't factor. So the fact that they're the same, what's one of my factors? 2x minus 7. And what's the other factor? Yeah, this leftover bit out front, x minus 7. I know it's x plus negative 7, but that's really just x minus 7. Whew. We did it. We factored. Now, again, there could be some people in here who factor differently. You might factor by just guess and checking. I know that that exists. You might just go ahead and look at the 2x squared minus the 21x and plus the 49. You might just look at that and start guessing. You might say, well, I know there's got to be a 2x and an x, and the only way to multiply 49 would be 7 times 7. And let's see, I need them to be negative. So you might just guess. Right? Is that possible? Did I just guess the answer? I did. Now, is that what I recommend you do in this class? Yeah. When you do work on a test, I really need you to show me your work about how you got your answer. So this would be the legit way of doing it, although guessing is just fine. It's just that you won't always be able to guess, will you? Sometimes the numbers will be so large and complex that you just can't guess. You really have to do this process. Okay, now what do we do? Yeah, set it equal to 0. This is called the zero factor property. Something times something equals 0. That tells you that either 2x minus 7 is equal to 0 or x minus 7 is equal to 0. Either way, if either of those things equals 0, the whole thing would equal 0, which is what we've been looking for. When will that original equation equal 0? So we go ahead and solve for x. One possibility is that 2x equals 7, x equals 7 halves. And then the other possibility is x equals 7. And what are those numbers? Roy? Yeah, they're the x-intercepts. So I could go ahead and draw myself a nice little picture. 7 halves is 3.5. 1, 2, 3, 4, 5, 6, 7. I've got 1 at 1, 2, 3.5. I've got 1 at 7. And can you all see the parabola in your mind's eye? You just kind of draw a little swoopy there, a little smiley face, a little parabola. And that's the end of our problem. We have now solved that quadratic. And we have solved it in a very thorough way. Not only do we know what numbers to plug into the equation to make it true, we also know what the graph looks like, which is very helpful. All right, folks. By the way, I didn't give you notes. The zero product rule. What does A times B equals 0 mean? Either what? Either A equals 0 or B equals 0. Sorry, I just realized that I hadn't given you that note. That's what the zero factor property states. If you multiply two numbers to equal 0, one of them has to be 0. All right. Now, folks, that was it for our second technique. The third technique is going to be everyone's favorite, completing the square. Completing the square. And in order to do completing the square, I would like to do a brief interlude and show you the parts and pieces of completing the square. So does everyone have this interlude page? It says, find each product using the double-it square it rule. And I think a couple of you were absent, but I think I gave you the sheets already. Does anyone need one? Because I do have some extras. Does anyone need one? No? Anybody? Because I have extras. You need one, right? Yeah, please, folks, let me know. Anybody else? There's actually two sheets. The other one also says solve each equation by completing the square. We're going to do these right now. Did you find it? Okay, great. All right, folks. So right up at the top, I say define the double-it square shortcut for a perfect square binomial. So first of all, how do you do x plus 7 squared? Then you have to FOIL it. So everyone, let's go and FOIL it. If you did FOIL it, it'd be x plus 7 times x plus 7. And when you do that, now see, I want us all to just memorize what the answer is. Because right now, you could just go ahead and tell me the answer is x squared plus 14x plus 49. But let's see how that shortcut works. When you do a square of a binomial, and you do first, outer, inner, last, it'd be x squared plus 7x plus 7x plus 49. Right, that would be your FOIL, first, outer, inner, last. And so take a look at, if I write down my answer of x squared plus 14x plus 49, where did I get the number 14 and where did I get the number 49? Yeah, this is 7 plus 7, and this is 7 times 7. And so that's the double it, square it shortcut. This is actually, if you write it one more time, x squared plus 2 times 7, x, plus 7 squared. So that you can see it a little more clearly. The middle term is 2 times 7, and the last term is 7 squared. So given that shortcut, you'd be able to very quickly solve all of these square binomials without actually having to do FOIL. So now go ahead and write down the formula. X plus a squared, the shortcut formula, is x squared plus 2a x plus a squared. And that's why I say double it, square it. Because we don't want to spend time doing FOIL every single time. We just want to know the shortcut. So as a for instance, I'll do this one, v plus 5 squared. V plus 5 squared. Automatically, the first term is v squared. And then I'm going to take my 5, I'll double it to get the middle term. So 5 doubled is 10. And then I'll square it. 5 squared is 25. And that's it. That's just our little mantra. That in your head, you could be saying, double it, square it. Now, if it's a positive number, that's pretty easy because it's positive. But how would a negative one work out? Like v minus 7 squared. Again, I start with v squared, but then I double it. What's negative 7 doubled? Negative 14. So that's a negative 14v. But then negative 7 squared is positive 49, because a negative times a negative is positive. So that's it. That's the double it, square it rule. Go ahead and write down the answer to all of those as fast as you can. Use the double it, square it rule. This is to build some muscle memory in your hand so that when you see scenarios like this, you'll just write down the answer without having to go through the steps of FOIL. Yeah. So that would be the middle term. What plus a squared? The last term is a squared. This is. There you go. Yeah, double it, sometimes 2, and then square it. Nice. Nice. What's negative 1 squared? You read that negative 1 times 2 is negative 2. But what's negative 1 times negative 2? Plus 1. Yeah, so that last one is plus 1. Okay. Should we compare answers on a few of these? I'm just going to call around the room. So I'm going to start with, let's see here. Diego, what'd you get for the first one?
B squared plus 2b.
Yeah, very good. 1 times 2 is 2, 1 squared is 1. Perfect. And then how about a minus 1 squared? David, what'd you get?
A squared minus 2a plus 1.
Yeah, very good. So -1 times 2 is -2, and -1 squared is 1. And how about, well, let's see here. Wait, Gloria? No. Grace? No, Gloria. Okay, Gloria, what did you get for b plus 7 squared? Yeah, very good. Plus 49. And then how about n minus 2, Jake? What do you get for n minus 2 squared?
N squared minus 4.
Yeah, very good. Okay, folks, so that's the doublet square root rule so that you don't have to keep on foiling when you see situations like this. It's more important than just a shortcut, though. This is now how we would turn around and go backwards. If somebody gave you a trinomial, so flip it over. If somebody gave you a trinomial, how would you then quickly factor it without having to go through the whole process of factoring? You know, asking yourself, what number multiplies to make the last number and adds to make the middle number? You could just confirm that it follows the pattern and then write down the answer. So how do we confirm that these problems actually are a square binomial? So here's the pattern I'd like you to check. For it to be double it, square it. First of all, let's look at 8. 8 is what number doubled? 4. So you take the middle term, you divide it by 2, that gives you 4, and then you square it, and does it equal 16? Yeah, that's the pattern we're going to do. You take the middle number, you divide it by 2, and then you square it, and it should give you the last number. And if that's true, then you can go ahead and just write it down as k plus 4 squared. And actually, I suppose what I should have done is 8 divided by 2 is 4, and then 4 squared is 16. So yes, it worked out, and the magic number is 4, as in it's k plus 4 squared. So how about the next one? You take the middle number, -4, you divide it by 2, which is -2, and then you square it, and does it equal 4? Yes. And therefore, the magic number is -2, and you can factor it as p minus 2 squared. This is if you have a hunch that this thing is a square binomial. You have to check to make sure it is a square binomial, and then you can go ahead and factor it as such. So how about this next one, k squared plus 6k plus 9? Anthony, what would I do?
6 by 2?
Yeah, take the middle term, divide it by 2, and then?
Divide 2.
Yeah, square it and check, and sure enough, it's correct. So what would it factor out to, Anthony?
K plus 9.
Not k plus 9.
K plus 3 squared.
Yeah, k plus 3 squared. Yeah, so it's that number in the middle. It's half of the middle term that's actually the term inside the binomial. How about Ayan? This one. What would you do? That is correct. That is the correct answer. How do we confirm that we really can do that? You take the middle term, divide it by 2, and then you square it, and it sure enough is 25. And so then you can go ahead and say it's p minus 5 squared. Yeah. Well, the thing is, you have to confirm that it even works. You have to confirm that it even works. For instance, if I just gave you a totally random trinomial like x squared minus 12x plus 30, can you just do half of the middle term and say, oh, half of -12 is 6, so I'll just go ahead and say x minus 6 squared. Can you do that? Definitely not, because I don't even know that this thing is a square binomial. And in fact, look, is -12 divided by 2 is -6, but -6 squared is 36. That number is not a 36. So this one doesn't even factor according to this method. So that's why, thank you, Gabby, for asking. You do have to show this work to check to make sure that this is even a square binomial. Does that answer your question? Okay. Okay, so how about another one? Robert, this one. How do I check first? Oh, no. Well, all right, let's do it together. You take the middle term and divide it by 2. So -8 divided by 2 is? 4. Yeah, -4. All right, then you square it. And what is -4 squared?
16.
16. Therefore, yes, this is a perfect square binomial. You can factor it. And how is it going to factor? All right, you take the middle number, or not the middle number, but this term here that got squared, that is the term that goes inside the binomial. So it'd be k minus 4 squared. So that's the process. Let's do that one more time. How about right here? How do you check? You take the middle term.
Yeah.
And do what?
You gotta find the square.
Well, not yet. The first thing you do is divide by 2, which is 5. And then you take it and you square it. Yep. And you just check. Is it actually equal to 25?
Yes.
Yeah. So all right. So that works. So now how do you factor it? It'll be x and then what? Plus 5. Yep. And that's it. That's how that works. All right, folks. We'll go ahead and continue factoring the rest. I'm just going to walk around, see if anybody has any questions. But this is very important that you're able to take that trinomial and factor it after checking that it actually is a perfect square trinomial. Oh. Did it work for you? Oh, great. Good. Nice. Very nice. So you just checked it in your head as well? Okay. Right. Go ahead and do this one. So you take the middle term, divide it by 2. Very good, and then square it. Negative 9. Well, positive 9. Negative 3 times negative 6 by 1. So we know that works. And now that number right there, if you want to underline it, that is the number that's going to be inside the perfect square binomial. So now it equals parenthesis. It'll be n minus 3 squared with parentheses. There you go. Yeah, that'll be it. Now, in terms of showing work, what I really recommend is that you take this middle number and then say, okay, take the middle number, divide it by 2, and actually show it. So 4 divided by 2 is 2. And then take that number, square it, and then check, okay, that's 4. Yes, that's 4. So it's kind of like a loop. You're making a loop where you go from the middle term, divide it by 2, square it, and check to see that it's really the last term. And then it's that number right there that goes inside the binomial. So it's going to be x plus 2 squared. And that's what you're looking for. So try that. Okay, folks. Now, what I just showed you is a whole bunch of trinomials, which you already, well, you know, we knew ahead of time that they were, in fact, perfect square binomials. But we do this process of checking to make sure that you really can factor it in that way. So how about the last few problems? Down here, they're saying, what would the last number have to be? Right? So there's just a letter C right there. But they're asking, what would the last number have to be in order for this thing to be a perfect square trinomial? So how do we find it? What would the number have to be? What's the process for finding out what the number would have to be? Yeah, the exact same process. You take the middle term, divide it by 2, and square it. So we'll go ahead and start with the first one. You take 26, and again, I like to draw these little arrows. I drop down my 26, I divide it by 2 to get 13, and then I square the 13, I get 169. That's what C should be. C should be plus 169. And when I say should be, I mean, if the value of C happens to be 169, then I can factor this thing into y plus 13 squared. And that's where the phrase completing the square comes from. We're trying to find what number to put at the end so that this thing is a perfect square binomial. And so we call it completing the square. So this process, we do this process all the time. I'll do it one more time. You take the middle number 18, you drop it down. 18 divided by 2 is 9. You square it, you get 81. That's what number you should put in the place of C. Because if C happens to be the number 81, then p squared plus 18p plus 81 can be factored into p plus 9 squared. So again, practice them. Give them a shot. Use that same process. Take the middle term, divide it by 2, square it. That's what number should go at the end. And then write it as a factor in the factored form of a perfect square binomial. Again, this is very routine. I realize this is just kind of a mechanical skill we're working on. By giving you this repetition, I'm hoping to build muscle memory in your hand so that you don't have to think about it so much every time you do it. You just do it. Take a middle turn, divide by 2, you square it, bam, that's the number. I like to show my number, so we can put it up like here. It's great. Let's get into it. You did it 5 times. I didn't know it was there. There. Your final answer is still the same. This is good. You just have to do that. All right, folks. Wherever you are, you can stop. This was just practice. It's okay if you don't finish all the way through. I'm not collecting this. It's just a skill builder. So now let's go ahead and review. Now that we have this knowledge about perfect square binomials and what they look like and what properties they have, now let's actually do completing the square, which is the third technique for solving a quadratic, which means finding the x-intercepts and the numbers that make it true. So what we're going to do is solve number 1 using completing the square. By the way, does everyone have this page? Because if you don't, I'll give it to you. Does anyone need it? Eric? Great. I'm so glad I asked. Folks, anytime you need a photocopy, please let me know. Anyone else need it? Okay. Of course, if I give it to you twice, I am charging you $5 per sheet. So Eric, you now owe me $5. All right, I'll get you for it later. All right. So folks, I want to solve b squared minus 10b plus 16 equals 0. First of all, can I factor it? As it so happens, I actually can. I could factor it if I wanted to. Just for fun, don't write it down. But this could factor into b minus 8 times b minus 2. So that does factor, in which case I already know my answer is b equals 8 and 2. So can you always do a different technique instead of completing the square? Of course you could. But right now we want to practice completing the square. So how you complete the square, I have all the steps right there for you. First, write the equation in standard form. Are we in standard form? Yeah. It goes b squared b no b. Move the constant term to the right and leave space. So everybody go ahead and move your 16 over to the right-hand side. And when you write it out again, b squared minus 10b, leave some space before you write the equal sign. Very important, you're going to leave a little gap there, leave some space. Because, of course, we're going to put another number there. Okay. Step 3. Find half of the b term. So I'm going to take my negative 10, I'm going to drop it down. I'm going to take negative 10, I'm going to find half of it, which is negative 5. And then I'm going to square it, which is 25. And that is the number I'm going to add to both sides. That exact same process that we were just doing. You take half of the middle term, square it, and that is the number I'm going to add to both sides. So plus 25, plus 25. I have now completed the square on this side. I have changed this trinomial into a trinomial that can be rewritten as b minus 5 squared. That was the whole goal, was to rewrite that trinomial as a trinomial that could be factored as a perfect square binomial. And what do I have on the right-hand side? 9. Well, folks, right there, just so you know, that's called completing the square. That was the moment right there. I took my trinomial and I turned it into a square binomial. Now, why is that so convenient, that I now have a square binomial? What can I do to finish solving this problem? The square root property. So now we just go right back to doing the square root property. We square root both sides and we get our answer. So to be fair, completing the square is just a step you do before you can use the square root property. So now we go ahead and square root both sides. I cancel out my square. Now I have b minus 5 equals, what kind of 3? Plus or minus 3, because that was an action step. We did the square root during algebra. Okay, so now we have b minus 5 equals plus or minus 3. I'm going to add the 5 over to the right-hand side. And now I have b equals 5 plus or minus 3. Does that look like the answer to a quadratic formula problem? Yes, because it's a number plus or minus a number. Okay, so now what I'll always do is draw my two little arrows. I'll say, well, in one reality, 5 plus 3 was 8. And in the other reality, 5 minus 3 was 2. And what do you think? Did I get the right answers? Yeah, I already confirmed it by doing another technique, factoring, to check to see that I got the same answer. And on a graph, those two numbers are my x-intercepts, 1, 2, 3, 4, 5, 6, 7, 8. There's one x-intercept, there's another x-intercept. There's my parabola, my happy little parabola. And now the problem is all done. So this is called completing the square. Now, we're not going to do all the problems on this sheet. I got a little excited and I put lots of problems for you to practice and try. But since the next one would be just like that, and I've got some harder ones for us to do later on, let's try number 4. Everyone, let's skip down and look at number 4. What do I have to do before I can complete the square? Multiply 3?
Or not to-
You're really close. I need my first term to just be n squared. I can't have a number on it. So how do I get rid of the 3? Yeah, I can just divide everything by 3, right? So everybody go ahead, get rid of that 3 by dividing all the way across. Everything gets divided by 3. And now it's just n squared plus 4n minus, what? 19? Okay. Now we can complete the square. Was that right, Brett? 19? No what? That is 19? Oh, you just used calculator. I was somewhat guessing. I was hoping someone was going to correct me if I was wrong. Is it 19? Okay. Yeah. Okay, so now we can complete the square. So let's try that process one more time. I have all the steps there waiting for you. What's the first step, Nancy? Nancy, right? What's the first step? You know, we go ahead and move the C term to the right. So I'm going to add my 19, move it over to the other side, and I'm going to leave some space. So I have n squared plus 4n, leave some space, equals 19. And then what's the second step? Myra, what's the second step? Yeah, take half of b. So I'm going to go ahead and take my 4. 4 divided by 2 is 2. And then I square it. That gives me 4. So 4 is the number I'm going to add to both sides. Very important, of course, that we add it to both sides. It has to go on both sides. There we go. So now, what's the next step after that? I am. Yeah, rewrite this as a perfect square binomial, which is? Yeah, very good. N plus 2, that was the middle number. So not the middle number, but the magic number right there, 2. And that equals 23. All right, so we've rewritten it now as a perfect square binomial. And now what's the last thing that you do? Let's see here. Julia, what's the last thing we do?
Just multiply by itself.
Well, that is telling us to square. But we don't actually want to square it, because then we would FOIL it out and we'd go back to the exact same problem we started with. What do we really want to do?
Square root.
Yeah, we really want to square root both sides. So that cancels out. We have n plus 2 equals the square root of 23. Is it just the square root of 23? Plus or minus the square root of 23. And then we subtract off the 2, and we get n equals negative 2 plus or minus root 23. And that's our solution, using completing the square. Now, even if I did my 2 little arrows here, what's the square root of 23? And it doesn't come out even. The square root of 23 is awfully close to the square root of 25. What's the square root of 25? 5. So what's the square root of 23? 4 point something? 4.9 maybe? 4.8? So just for fun, I'm going to go ahead and say negative 2 plus 4.8 and negative 2 minus 4.8. And that's giving me a rough approximate answer of 2.8 and negative 6.8. Now, obviously, I should use a calculator. I shouldn't just do that off the top of my head. But at least now I have a rough idea of what my parabola looks like. I've got one intercept at 2.8. I've got one intercept at 1, 2, 3, 4, 5, 6.8. And there's my parabola. Yes, sir, Uriel.
Is it good to leave it as root 23?
Absolutely. Yeah, the answer is -2 plus or minus root 23. I think that's what the back of the packet would say. Normally, folks, great question, Uriel. Normally, we would just leave our answer like this. It looks nice and clean. But when would you want a decimal approximation? If you wanted to graph it, or if it was a word problem. If this was a word problem, and the problem had been, you fire a toy rocket into the air, after how many seconds will the rocket land? Okay, so if my question was, after how many seconds will the rocket land? First of all, which of these is the right answer? Get the positive answer. Okay, a rocket won't land -6 seconds later. A rocket would land 2.8 seconds later. And you would want to know the 2.8. Because if you walked up to somebody and said, hey, that toy rocket is going to land at -2 plus root 23 seconds. Yeah, they would slap you. They would go, what? What's -2 plus root 23 seconds? Be nice. Be human. Tell me 2.8. Right? So we use decimals if you want to actually answer a word problem or if you want to graph it. But otherwise, thank you, Euro. You would just leave your answer as -2 plus or minus root 23. Okay, folks, I think that's enough for our example of completing the square. Let's go ahead and go back to our packet. Our notes packet. Let's go back to the notes packet. You have now those notes. It tells you step by step what to do. In fact, I would keep that out so you can continue looking at the notes. Or you could go ahead and write them down again on this page. I could be wrong, but your midway quiz, folks, your midway quiz is going to ask you to do one of each of these. So when I give you that quiz tonight, you're going to have one of each of these problems to do. And the beauty is, can you use these nicely written steps to complete your quiz? Yes, you can. Can you use another human to help you with the quiz? No, but you can use these steps to help you. All right, so is this our next section? Are we on number 25? Okay, so number 25. Solve the equation by completing the square. Recall that nice fact I told you. So, how do we complete the square? What's our first step? I'm gonna go around. I'm continuing to learn people's names. Ryan. Ryan, what's the first thing we do in completing the square? Yeah, move the 24 over. So we have x squared minus 2x, leave some space, equals 24. So I move my 24 over to the other side. I quote unquote move it. I added 24 to both sides, and now it's a positive 24. Okay, what's the next thing that we do, Allison? This is essentially where all the work happens. Yeah. So what do?
You have to divide.
Yeah, take the middle term, divide it by 2, you get -1. And then? And then do what? Allison?
Oh.
And then?
And then you square it.
And then you square it, and you get 1. And then what do you do with that 1?
Put it up there.
Yeah.
You add it to both sides.
Very good. Thank you very much. So you add it to both sides. Super. That whole little loop that I just showed right there, that is the work that I'd like you to show. That shows exactly what you're doing to your audience. All right, so now what do we do? Oh, let's see here. Let's see. I don't talk to everybody today. Maybe. Jose. Now what? We can combine what's on the right, so that's 25. What do we do now with what's on the left?
You
Yeah, exactly. You go ahead and rewrite it as a perfect square binomial, which is x minus 1. You got that from the -1 that we squared. So now we have x minus 1 squared equals 25. And now what do we do, Uriel? Yeah, square root both sides. We have x minus 1 equals plus or minus 5. And then now what do we do, Brett? Yeah, add the 1 over to the other side. And now we just have 1 plus or minus 5. All right. Now, going back to Uriel's question, would we leave our answer like that? No, that would be silly, right? I mean, these are just whole numbers. You can easily add them together. So it's just when it's a root that you can leave it. But so we have 1 plus 5, which is 6, and we have 1 minus 5, which is -4. Now, folks, the fact that I got such nice, clean answers, what does that tell us about what other method we could have used? The fact that they came out to be nice whole numbers, what could we have done? We could have factored. right? When the answers turn out to be nice whole numbers, that tells you could have factored. And indeed, what numbers multiply to make negative 24, that add to make negative 2? That'd be 6 and 4. So it'd be x minus 6 and x plus 4. We could have factored that problem. I mean, yeah, we could have. But keep in mind, on the quiz or on the test, if the instructions say to solve by completing the square, you have to complete the square. In the past, I've had people have a problem that says complete the square, and they did the quadratic formula instead, and I gave them no credit. Because the point is not to get the answer. The point is to demonstrate the solution method that was asked. So make sure that you're using the right technique, even though you could factor. All right, folks, this is our last completing the square problem. This one is quite challenging. So let's buckle down and do one more example. Can I complete the square right now? Can I go ahead and just move the 3 over? No, what's wrong right now? Yeah, that 2. We've got a 2 right here. So what do we have to do with the 2? We have to divide it off. Dividing off the 2 right now is a bummer. Why is it a bummer? Yeah, we now have all sorts of fractions, and I'm going to leave them as fractions, and I hope you do too. Absolutely, you could do it with decimals. You really could. You could do this whole process with decimals, and in fact, if you prefer that, you could. But we're going to leave it as a fraction. Now can I move my 3 halves over? Yeah, now I can go ahead and move my 3 halves over. So you start by moving the term over. So now we have x squared plus 7 halves x equals negative 3 halves. Now, folks, the first thing you might be asking is, oh, no, these are fractions. I'm not a big fan of fractions. I'd rather do decimals. Why are we going to leave it as fractions? Because that's the form of the quadratic formula. The quadratic formula is fundamentally one big fraction. So we want to leave our answer as a fraction because that way when we're done, it will look the same as if we had done the quadratic formula rather than a whole bunch of decimals. Okay, so we start our process. We take 7 halves and divide by 2. What's 7 halves divided by 2? You could type it into your calculator. It is 7 over 4. Let's just remind everyone so you see it. 7 halves divided by 2 is really 7 halves divided by 2 over 1. And how do you divide by a fraction? How do you divide by a fraction? Multiply by the reciprocal, which is really times 1/2. And therefore it is 7/4. So that's 7 halves divided by 2. So you could go ahead and write it down anyway. 7 halves divided by 2, which is really 7/4. And now you take your 7/4 and you do what, Troy? Square it, which is, how do you square a fraction? You square both the top and the bottom. You square them independently. So 7 squared is 49, and 4 squared is 16. And that is the number we get to add to both sides. So I'm going to add 49/16 to both sides of our equation. Now you notice we're still doing the same process. We're doing the exact same procedure. It just so happens that there are fractions involved, but we're still doing the exact same procedure. So on the left-hand side, how does this factor into a perfect square binomial? It would be x, what goes right here? Yeah, 7/4, the number that you squared. That's always how it goes in the process. It's the number that gets squared. So it's x plus 7/4. And now how about over here? What's negative 3 halves plus 49/16? Yeah, you have to, well, combine like terms, you need a common denominator. Yeah, I know what you're saying, Gabby. You need a common denominator. Now, you can use your calculator if you want. You could type in negative 3 halves plus 49/16, and your calculator actually has a button, so you can get the answer as a fraction. But we'll go ahead and do the work. The common denominator is 16, so that's going to be negative 3 halves plus 49/16. So I have to multiply this one top and bottom by 8. That gives me negative 24/16 plus 49/16. And negative 24 plus 49 is 25/16. Whew, what a great number. 25/16. Why is 25/16 such a great number? They're both square numbers, right? That's very handy and convenient. Why is it so handy and convenient that they're both square numbers? What are we about to do? We're about to square root both sides. So that's really nice that it worked out to be that way. So, just waiting to click. These people are still writing. Now what? We square root both sides. And so now we have x plus 7/4 equals plus or minus the square root of 25/16. How do you square root a fraction? You square root the top, square root the bottom independently. Just like you square a fraction by squaring the top and bottom independently, you square root a fraction by square rooting them independently. So the square root of 25 is 5, and the square root of 16 is 4. So we now have x plus 7/4 equals plus or minus 5/4. And so how do we finish the step, right? X is being added by 7/4, so you would subtract 7/4 from both sides. And so now, folks, we have x equals negative 7/4 plus or minus 5/4. Now, do we just leave our answer like that? No, because we can actually do this. Right? If it was a root, you could just leave it. But it's not a root, so we have to calculate it. So again, I'll use my two little arrows, and I'll say negative 7/4 plus 5/4, or negative 7/4 minus 5/4. And so I get negative 2/4, which simplifies to negative 1/2. And I get negative 12/4, which simplifies to negative 3. Whew, boy. Now, admittedly, that was a lot of work, wasn't it? Do you think in the future, if you saw a problem like this, you'd think, hey, I know, I'll do completing the square? Anyone? Probably not. What would be your go-to method if you had to do this problem? Probably the quadratic formula, right? The quadratic formula, boom, 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 you plug in all the numbers, you're done. Probably no one on earth would look at this and say, I'm going to do completing the square. That sounds like fun. No. No. Probably you would do the quadratic formula. But it's still a great technique. So, I believe that's it for completing the square. Now we're on to the quadratic formula. Yay! Quadratic formula. Folks, truly, this was a massive review. We just, in the last hour or so, we are completely reviewing all the techniques you've ever learned for solving a quadratic and thinking about what that even means. This is a big review. I wouldn't be surprised if after this you feel a little tired and need to go home and take a nap. Because it's a lot to review. Okay, I'm going to leave that up there just in case you're still looking at it. Let's go ahead and do the quadratic formula. The quadratic formula, you all know that negative b plus or minus x squared b squared minus 4ac over 2a. My biggest recommendation is this. First, you want to write down what your a, b, and c values are. So you would actually identify them. You'd say a is equal to 1, b is equal to negative 14, and c is equal to 53. So you begin by just identifying them nice and clear. The next thing that you would do for your brain and for your audience is you would write down the quadratic formula once. You'd say, okay, negative b plus or minus the square root of b squared minus 4ac all over 2a. You write it down because that's not the type of thing you just want to do off of memory. Just like start plugging numbers in without even having a formula to look at. That's very challenging. Okay, but now here's my biggest advice. And we'll do this throughout the semester. You're going to write that formula empty. Write it empty. Now, what does that even mean? Write it empty. Yeah, exactly. Everywhere you see a variable, you put a little open parenthesis. Just a little open parenthesis with nothing inside. So I'll even say it. I would say negative parenthesis plus or minus the square root of parenthesis squared minus 4 parenthesis parenthesis all over 2 parentheses. So everywhere you see a letter, you put a parenthesis. Now, why is that nice? Because what can you do now? You just plop in all your numbers, right? You drop in your numbers. More importantly than it being nice and tidy and clean, that's how you'd have to type it into your calculator, right? Your calculator needs all those parentheses. If you type that into your calculator without parentheses, it's going to miscalculate something because there's lots of negatives, and all those negative, like this negative 14 right here, all those negatives have to be calculated correctly by your calculator, and so you need parentheses. Okay, so now let's drop in all of our numbers. We would have in a negative, that's not very It might work. Negative 14 for B. Negative 14 for B. A is 1. C is 53. And then A again is 1. So now, we do this very carefully. You very carefully look at every term and ask yourself, all right, what do I have? So first, negative 14 is really just 14. And then plus or minus the square root. I'll just do a couple computations at a time. Negative 14 squared is 196, which you would just type into your calculator, negative 14 times negative 14, minus 4 times 1 times 53, which is 212. And again, you type all those things in your calculator, one little computation at a time. And then that's all over 2. Now, I realize, you could have gone ahead and typed in 196 minus 212 and then wrote that down, but it's really helpful to just do a couple computations at a time. So now I have 14 plus or minus the square root of negative 16 all over 2. Now, hey, wasn't that exciting that it turned out to be 16? Why is that so exciting? Because you can square root 16. Now, you can't square root at negative 16, but you can because you can pull out the I. So now, we go ahead and square root the negative 16, 14, plus or minus, the square root of 16 is 4, the square root of negative 1 is I, so that's 4I all over 2. Now at this point, you could just go ahead and divide the 14 and the 4 by 2, because they're both getting divided by 2 and you can cancel everything. Or if you wanted to be super legit about it, you'd break it into 14 halves plus or minus 4I halves. That way you can really see why you're allowed to cancel the 14 with the 2 and the 4 with the 2. So what does that give us? 7 plus or minus 2I. If right here you had said 2 goes into 14 7 times, 2 goes into 4 twice, 2 goes into 2 once, that would have been fine. You can do that. You'd still get the final answer of 7 plus or minus 2I. Where are the x-intercepts? There aren't any, right? There are no x-intercepts. Technically, this parabola is floating up above the x-axis. But are there solutions? Technically, there are solutions. If I plug 7 plus 2I into that equation, it will make it true. If I plug 7 minus 2I into that equation, it will make it true. It's just that the parabola is floating above the x-axis. So there's no x-intercepts, but there are solutions. That's a little subtle. All right. Well, I'm going to leave number 28 for you guys to do, because you just put it in standard form, plug in all the numbers. But let's go ahead and take a look at this last chunk about the discriminant. The discriminant. Have you heard this word before, discriminant? Discriminant is a little funny of a word, discriminant. What word does it sound like? Discriminate, right? And discriminate has somewhat of a negative connotation because to discriminate against someone means to treat them poorly because of some prejudice you have, right? So discriminate sounds like a bad word. But discriminating, like a discriminating taste. I have a discriminating taste in fine wine. I have a discriminating taste in good pizza. What does that mean? It doesn't mean that I'm judging wine and judging pizza. It means that I have the ability to distinguish between really good pizza and really bad pizza, right? So have you heard that, the word discriminating in that way? To discriminate simply means to tell the difference between what's what. This is one type of pizza, this is another type of pizza. So when we talk about the discriminant, we are really using the word discriminant to mean that we're discriminating between 1 or 2 or 3 different cases, okay? We're not judging anything. We're just discriminating between option 1, option 2, and option 3. And so, all that said, what do you suppose we're discriminating between? What are we going to discriminate between? Yeah, the different types of parabolas that we're looking at. For instance, a parabola that has 2 solutions versus a parabola that only has 1 solution versus a parabola that has 0 solutions. Although it's not really 0 solutions. What are the solutions? Imaginary. So, you don't have this drawing on your paper, but if you just wanted to draw it real quick, you could. In fact, I think that'd be a good idea. Didn't I leave you some space? I said evaluate the discriminant, then use it to predict the number of distinct solutions, whether rational, irrational, or non-real. Yeah, let's all draw this together, folks. I gave you a little space there so that we could all draw together. And in fact, I'll even start over so that I'm drawing what you're drawing and you're drawing what I'm drawing. So you've got your space there. First thing I'd like you to do is go ahead and draw one parabola where it does cut through twice. And then draw another parabola where it only cuts through once. And then go ahead and draw another parabola where it floats above the axis. So that's the space that I gave you, so that you can draw these little pictures with me. So how do we discriminate between these three cases? Well, we know that when we solve the problem using the quadratic formula, for instance, I either get two answers, or one answer, or imaginary answers, right? But I don't want to have to get all the way to the end of the problem in order to figure out what kind of parabola I'm looking at. I want a quick test to see which kind of parabola am I looking at. So let's start with this one, actually, because this one's actually the most obvious. When looking at the quadratic formula, okay, so I'm just going to write it down right here, negative b plus or minus the square root of b squared minus 4ac all over 2a. When you do the quadratic formula and you get a situation like this, what goes wrong? What part of the quadratic formula goes wrong that we know that the parabola is floating above? Yeah, we square root a negative, right? If you're square rooting a negative, that means it's imaginary, which means there are no x-intercepts because the parabola is floating above. So the first thing we could go ahead and say is, if b squared minus 4ac is negative, then that's the type of parabola we're going to get. And I just write b squared minus 4ac is less than 0. But what that really means is that b squared minus 4ac is negative, which means you're square rooting a negative, which means it's imaginary, which means it's floating above. So if b squared minus 4ac is less than 0, we will have two imaginary solutions. Right? Like, for example, you would have x equals 2 plus or minus 3i. And you can tell that just by looking at b squared minus 4ac. You don't have to calculate the entire quadratic formula. All you need to do is just calculate b squared minus 4ac. And whatever that number happens to be, like for instance, let's say that b squared minus 4ac ends up calculating out to be negative 4. Well, you already know that because that equaled negative 4, it's negative, so there's two imaginary solutions. All right, what about this one? This one might be a little more tricky. When would because did we even see one of these today? I don't think we even saw one of these today. When would there only be one answer? And again, focus on the plus or minus. Plus or minus gives you two different answers, doesn't it? So when would there only be one answer? What would that whole thing have to be so that you're not really plus or minusing anything? It would have to be 0, right? If b squared minus 4ac was 0, you're square rooting 0, and then you're doing plus or minus 0. Does plus or minus 0 give you two different answers? Like what if I had negative 2 plus or minus 0 all over 1? What would my two possibilities be? Negative 2 plus 0 over 1? Or negative 2 minus 0 over 1? What does that give me? It really gives me the same answer, right? So when will a parabola just touch down on the line to give you only one answer? When what? When b squared minus 4ac equals 0. That will give you one solution. So when b squared minus 4ac equals 0, there's only one real solution. It is real, right? Not imaginary. It's not imaginary because, you square root it to 0, that's fine. You can square root 0, it's just 0. And if you plus or minus a 0, it doesn't really create two different numbers. It really just creates one number. So when b squared minus 4ac is 0, you already know that there's just one solution. We got 5 minutes. Let's finish this. So then what's the other possibility? B squared minus 4ac is either negative, or B squared minus 4ac is 0, or B squared minus 4ac is positive. So that's the third case. If B squared minus 4ac is positive, well, then that means we actually are plussing and minus something different. If I actually truly do, like say, have the square root of 16, then I really am either going to add 4 or I'm going to subtract 4. And that's genuinely going to give me two different solutions, won't it? So if you square root a positive number, you actually are doing a plus or minus. You actually are generating two alternate realities, and therefore you're generating two different answers. So that's two real solutions. So what do we call this thing, b squared minus 4ac? That's the determinant. The determinant is the b squared minus 4ac. It's the part of the quadratic formula that actually determines what type of solution you have. Okay, so everybody, you all just drew that information in right here. So in terms of just a definition, the b squared minus 4ac, just that term right there, is the determinant. And just by calculating it, you don't have to do the whole problem. You don't have to do the whole problem. All you need to do is just calculate b squared minus 4ac, and you can immediately know what kind of parabola you're looking at and how many solutions you should get. So let's try it real quick. I think, yeah, I'll just try one with you. I still have 4 minutes. So I've got here a equals 1, b equals 3, and c equals -4. So that very first example there. S squared plus 3s minus 4. We'll go ahead and calculate b squared minus 4ac. And again, I recommend you write b squared minus 4ac empty. So that's really b squared minus 4ac. So I wrote it down empty, and now I'm going to go ahead and plug in my answer, or my numbers. So that's b squared minus 4ac. And this gives me 9 plus 16, which is 25. So what is my discriminant? What type of parabola am I looking at? Yeah, 2 roots. This is what I'm looking at. I already know, without doing any more work, that I'm looking at a parabola that cuts through the x-axis twice. I'm going to get two distinct answers. And that's the benefit of the discriminant. So I'll go ahead and say 2 real answers. And that's it. That's how you use the discriminant. The beauty of the discriminant is that you can almost do it in your head, right? You wouldn't do it in your head for a test because you wouldn't get any credit. But I can do this one in my head. B squared is 4 minus 4ac is 0. So I just did the discriminant. It equals 0. So what kind of parabola am I looking at? This one. Now I know that that parabola only touches down once, and there's only one answer. I'll do this one in my head. B squared is 4 squared is 16. Minus 4 times a times c, that's 20. 16 minus 20 is a -4. Therefore, I know I'm looking at a discriminant which is negative, so there's 2 imaginary solutions and my parabola is floating up above the axis. So that's it. 1 real answer and 2 imaginary answers. Now, what would really make your answer pop? What would really make these answers look good? Well, you could solve them all the way through, yeah. You could finish the problem. But I mean, what's something quick and easy you could do for your audience to make it even more obvious? Yeah, draw a quick little picture, right? Just a little doot-doot, and a little doot-doot, and a little doot. Now, doesn't that really make it look better? This looks better, folks. This looks great. That really communicates to your audience that what you're trying to tell them. Because if you just tell someone, yeah, there's 2 imaginary solutions, they might look at you and be like, what? So what does that mean? I don't know what that means, 2 imaginary solutions. And then you say, the parabola is floating above the x-axis. And they're like, oh, okay, the parabola is floating above the x-axis. I get you. All right, folks, your midway quiz. Your midway quiz has a percent problem, a square root property, a factoring problem, a complete the square problem, and a quadratic formula problem. Now let me ask you, for each and every quadratic problem that you do, what do you guess I want you to draw? I want you to draw the graph. I want you to show me a little sketch about what that graph looks like. So of course I want you to tell me the answer, you know, x equals 5 and -3, but I definitely want you to draw a picture because that picture will really make your answer pop. You know, you go into a job interview and everyone in the world is writing down the correct answer, but you draw a graph? Oh, you just got hired. Did I ever collect your syllabus quizzes and personal information? Yeah, I'll make those. Folks, if you would, please bring up your syllabus quiz and your personal information. And we'll start a little stack right up here.
Can I ask you a question?
Yeah.
This one here, I can find the answer to.
Oh, you know what? I don't think I. Folks, did anyone find the answer to? Did we review this yet together? Oh, geez. On the day of the test, the online math lab homework, if it's not done on the day of the test, if it's incomplete, you can continue working on the remaining problems for a 30% deduction. So you can keep on working after the due date, but I'll take off 30% for any of the problems that you did late. So you still get full credit for the problems you did before the due date, but after the due date, you lose 30%. Yeah, but I didn't collect it before because I said we were going to review it. But now we don't have any time. So folks, it's up to you. Should you hold on to it until next class and then we'll review it, or should I just take it? Just take it. Come on up here and bring it up here, folks. All right, folks, thank you very much. Did everyone get a midway quiz? Did everyone get one?
What did you want us to graph on here?
Good question. On the midway quiz, you should provide a graph for number 2, 3, 4, and 5. Number 2, 3, 4, and 5. You should just provide a sketch. Just a sketch, folks. It does not have to be a beautiful, perfect graph. It just has to be a sketch.